I'm actually not sure which one that is, so it might be a student or something close to that. Okay. Oh, I know that one. That's just a revision. Uh, all right. Well, I'm so excited to be here, and I've enjoyed talking to you all a bit so far, and I'm looking forward to talking to you all for the next several days. Um, Also, please interrupt me, so I'll probably be like staring down at my feet nervously and not notice, but just shout out if you have a question. Um, so what I thought I'd try to do today is basically pick up, I'm going to try to pick up from Ruben's lecture the other day, when I think he introduced basically the objective functions for reinforcement learning, right? Like what will we be trying to do in a sequential decision problem? What are we trying to optimize? And a sort of idea of some discounted future reward or something like that. What I thought I'd try to do today, okay, this doesn't work, is really think about how it is, both kind of mostly at a process level, but also at a kind of neural level, how the brain could actually compute these quantities, particularly something like an animal and kind of trial and error learning. So that in computer science, of course, this is known as reinforcement learning. So trial and error, sequential decision problem optimization. And I think it's great to sort of pick up on the first lecture from Ruben, because while he stated the problem, it's really hard to solve it. And so what I thought I'd like to do is talk about sort of two approaches for solving the problem that is sort of classically used in reinforcement learning and AI, and which I think give us a sort of handle on thinking about different ways the brain can approach this problem of learning to make choices sort of optimally in sequential tasks. And they're known as model-based and model-free learning. And actually, because now Uchida is going to talk, give, I think, basically 2 lectures about model-free learning in the brain and dopamine and so on. I'm going to focus mostly on the other part, the model-based. So I'll talk a little bit about this, but mainly I'm going to focus on not disagreeing with now, but sort of adding to it. I think there's more going on than what you're going to hear from now. And so I think these 2 lectures together, or these 3 lectures together, will hopefully help you see a bigger picture. So basically what I'm going to do is talk about, depending on how much time we have or how far I get, sort of 3 examples that illustrate in different cases spatial navigation and animal lever pressing and humans playing decision games. This sort of distinction between these 2 types of approaches to reinforcement learning and why we think that the brain uses some of each. And I think that Lucia tomorrow will have one more, so I think there'll be a 4th. So what I hope is that it may be a little bit vague at first. I hope that the examples, just by sheer repetition, sort of will help us sort of see concretely what we're talking about here. And then between sometime between the end of today and Saturday, I'm going to be talking about sort of more neural things about the hippocampus, how it might be involved in these processes, and also some stuff about the entorhinal cortex that really relates to the soft RL idea that Ruben gave us yesterday or the day before. Okay, so that's the plan. So just to remind you, this is the kind of setting that we have in mind, right? So this is, I think Ruben had this figure, this is a Sutton and Bartow figure. The concept is you have this world, the world has states and rewards. The agent sees the state and reward, takes an action, and the environment gives him another state and reward. And so these are Markov decision problems, sequential decision tasks. And the key issue here that makes it sort of difficult is that choices aren't immediately rewarded. They lead to more choices. And so the consequences of your actions can sort of play out gradually, like in a maze or a game of chess or something. And we have this value function, right, which we talked about last time. So why is this hard? I think the main reason this is hard, and this is the thing I'm going to focus on today, and then Saturday I have a slightly different take, but the main reason this is hard, again, is that basically in order to decide what to do, whether it's in a spatial maze or a game like Go, or this is a video game called Montezuma's Revenge, when you consider a possible course of action, like placing a stone here or here, or jumping this way or that way, or turning left or right, whether or not that's useful is going to depend on outcomes that come many steps later, and might be contingent on later choices and later things that happen. And so one way of thinking about just abstractly the problem of choosing in this kind of a task is it requires sort of connecting actions to their consequences over kind of long distances of space and time and sort of multiple contingent probabilistic steps. So sometimes this is called credit assignment if you're thinking about it in terms of learning. Sometimes it's called planning if you're thinking of sort of forward. But either way, you've got to sort of draw a line from something you do now and something you get later. So that makes trial and error learning really hard, of course. So the reason I use this example, so this is DeepMind had trained neural networks using reinforcement learning to play a whole series of video games. And this one was the one that it failed at. It was good at most of them, but it was terrible at this one. And it's because one of these keys opens a door several screens away. So the computer had to discover that picking up this key was, even though you could get killed by this skull, picking up this key was a good thing, and only several screens down the line did it do anything, which was open a door. And so that's a very difficult credit assignment problem, learning that it's worth grabbing that key because much later that can help you earn points, right? So that's a difficult trial and error problem. But I also want to point out, even if you know everything about how the game works, there's nothing to learn by trial and error, like you know, or you might know the rules of Go or chess, or a complicated maze, it's still really hard, right, to figure out what to do. So even if you take out the learning part, the sort of planning part is still difficult, just because there's so many possible paths through the world. Okay, so that's the sort of abstract version. And you can also see that in the math, right? So this is a version of an equation that Ruben showed you several versions of as well. I said Q instead of V, so if it's conditioned on state and action, then it's called a Q function instead of a V function, but it's the same idea. It says if I'm in some state and I choose some action, I want to know my expected cumulative sum of future rewards. I left out the time discounting here, but it's an expectation over a branching path through future states, right? And that branching path could be very deep and very broad. And so you can just see the sort of tree that's implicit in these nested sums is going to be really hard to evaluate in general, even if you know the one-step contingencies. You just can't sort of visit all of the boards of Go. So you can just see in the objective function it's going to be a hard problem. That being said, and I think Ruben mentioned this also, if you knew this, right, if I had an oracle or a table that I could look up, I'm in some particular configuration of Go, how good is it to put my stone here, 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 here? Choice would be easy, right? That table would flatten this sort of long nested sum, and it would tell me what to do in terms of the expected future reward, right? So that's why estimating the value function is often a sort of subtask in reinforcement learning to solve these problems. Is that clear? Good, so that's all sort of set up. So again, what I'd like to try to do today is talk about how in practice we might try to go about, or the brain might try to go about solving this problem. And there's basically, I don't want to suggest a very strong dichotomy here, but I think it's useful to think about two approaches. There's many in-betweens and so on, and we'll talk about that. But there's sort of two broad approaches that you might think about as sort of working on the left-hand side or the right-hand side of this equal sign. And now is going to talk about one of those as well. So the first version, and this goes back really to the first work on checkers players and so on in AI in the 50s and 60s by Samuels, is what's now known as model-based learning. And the idea is, again, if you know the rules of Go, that is, you know which moves are legal and how they lead to changes in the board configuration and how that ultimately leads to different winning configurations at the end of the game, then in principle, that's essentially this probability function, right? I left the max out of this, by the way, that Ruben talked about. We'll come back to that on Saturday. But in principle, and it's a big principle, if you knew this function R, which is basically an indicator for which board positions are winning, and you knew this P, which is about sort of how different moves, which moves are legal and how they change the board, then solving this problem, of course, is, or starting from some configuration, in principle, all you have to do is work through the tree of future states, just summing up, seeing where you find rewards and adding them up, right? So if you know the structure of the game, the sort of local kind of one-step changes and how likely they are and so on, another example would be the map of a maze, then you can use that iteratively to work out these iterative sums, right, and literally add up the value function, at least over a small domain, right? Now this figure is from this AlphaGo paper, again from DeepMind, and this is actually how it worked, more or less. Of course, they can't search every possible path through the game, but they searched many different paths through the game and estimated this equation, and that's how they developed sort of superhuman Go player, again, through methods that basically go back to earliest kind of checkers players and chess players in the beginning of AI. Yeah. No, they also have neural networks at various points. So there's function approximation as well. Yeah, I'm not going into the details, but yeah. So they have neural networks for predicting which paths to follow and so on, and also for evaluating partial boards. Yeah. I'll come to that soon. But let's, what the model is then. So the reason this is called model-based learning is that if you know these two functions, the transition function and the reward function, that's sometimes called an internal model of the task, right? So if let's say I didn't know how to play Go, or I'm exploring a maze, if I could memorize all of the junctions in the maze, how locations lead to other locations if I turn left or right, where there's cheese, or the rules of chess, or so on, that's a learning problem, right? That's actually a relatively easy, a learning problem that's a relatively easy learning problem in the sense that it's sort of Hebbian, right? It's just local information. All you need to know is how things relate to things over a single time step, and that's the model. And then the hard part is iterating that model over multiple steps to add up the reward. So the model learning part is hard. The model learning part is easy. The model planning part is, sort of laborious iterative computation, right? So that's model-based reinforcement learning. So in the case of at least the original AlphaGo, they didn't learn the model, they just programmed it, but later versions learned it, and that's why it's called reinforcement learning. And here's how well it did, just to give you a feel if this works. So these are these sort of ratings, like chess ratings, ELO ratings. So this poor guy, Lee Sedol, was one of the human masters, and there's a movie in which DeepMind beats him in a tournament, and he goes into retirement, and humanity is embarrassed. And meanwhile, the system gets even better, and it's now sort of superhuman. That's a good movie, by the way. It's a little depressing if you like humanity, but I don't, so it's fine for me. Okay, so that brings us to model-free learning, and it's the same equation, and here's the idea. So there was these sort of papers that said, you've heard about the curse of dimensionality, maybe, that problems are very high dimensional. People have also talked about the curse of modeling, that figuring out how a complicated system works is a hard problem, and it would be great to skip that and just learn the long-term value function, estimate that directly. And so the slogan for that became model-free learning. So the idea is, that if you think about, instead of working on the right-hand side of this equation, where I take all these sort of short-term quantities and string them together to compute the long-term quantity, if in some way I could focus on estimating the long-term quantity, this rewards until the end of the game, and sort of fill in a table or a function approximator or a neural network that gives me back for a state in action, just retrieves this long sum, then I'd be in good shape, right? Because then I could just ask it what to do, or what's the long-term value of each step, and I wouldn't have to do all that iterative thinking. So that makes the learning problem much harder, because you've got to learn not individual local things, but a long sum of things, and so it's hard to collect data and so on. But there are algorithms to do this, and again, I'll talk a little bit more about this, and now is going to, I think, talk about this for 2 days. Temporal difference learning is sort of famous in neuroscience because it's associated with dopamine, and what the advent of temporal difference learning showed us is it's actually possible to directly learn estimates, like train a neural network or a table, to estimate the long-run value of the actions in terms of sums of future rewards from experience without representing the individual steps of the computation, the rules of chess, the one-step rules of chess or the one-step rewards. You just take samples of the entire function or estimate samples of the entire function and learn that p-value. And so that's how, sorry, yeah. Mm. I think we're gonna, I think I'm probably heading in the same direction as that. Maybe, I think if by the end of today, or at least if I get to the end of today, I haven't backed off that far enough for you, we can talk more. I think it's helpful, historically, and for reasons of data I'll show you, historically people really thought there were 2 separate things in the brain. And I think there really are 2 separate types of computation here, right? There is either experiential learning from trial and error sequences, which give you samples of Q, and there's sort of mental simulation from knowing how the world works. Whether that's really 2 distinct separate modules in the brain or their various intermediates, I think we can come back to. But I think it's helpful to understand those 2 building blocks, basically, to think about this problem. But yes, I think lots of people rightly are uncomfortable with thinking of this as a very tight, as a very strong dichotomy, and there's various ways it could be blended more in various hybrids. But I think it's helpful to think about it as 2 separate things to understand how it works to start with. Okay. So this is the example, again, from DeepMind. Yeah. Well, to get the model, you probably need experience too. Yeah. Well, but still. Yeah, so I think Go is a good example of a case where once you know the model, you can infer things about positions you've never seen before, right? And so that's one reason model-based learning is useful, is sort of transfer to situations, to board positions you've never seen before. Model-free learning is perhaps useful because in the case where you have seen the board before, so these Atari games are deterministic, and so you can sort of visit every possible screen in them. You can just, once you have enough knowledge, you can just compile a table of these things, you don't have to do any more thinking, right? But again, you can put, you can use experience in different ways, and you can combine planning or model rollouts with storing of long-term values, right? But there's sort of 2 mechanisms. And historically, they have tended to be used in AI, one or the other, or mostly one or the other. The Atari games, they basically give video input to a neural network, it makes joystick movements, and the rewards are points, and it literally uses temporal difference learning through backpropagation and some tricks to learn to play all these Atari games, and it mostly works. And the way temporal difference learning is, I'll talk a little bit more about how it estimates this long-range quantity from short-term experience, but I think now is basically going to focus on that, because it's a story about how dopamine works as well. Yeah. Yeah. Mm. Well, we don't have to. So I think the way that one would talk about this in AI is they would distinguish the objective function and the target of the learning from what's called function approximation, right? So I might not fill in a table with a set of discrete actions and a set of discrete states. In fact, the way this works is it's a neural network, right? But it was still useful for them to train the neural network to have a objective function that's written in terms of a Markov decision problem that satisfies certain conditional independence properties and so on. And I think it helps you reason about what it is you're trying to do and how to solve the problem. That is not to say that what you literally have is a table of this board position and this discrete movement of the joystick and so on. So you can have continuous, features and stuff, and multi-layer neural networks, and that's how this actually works in AI at this point. But I think the formalism is still useful, at least as an abstraction, again, to sort of think about. Good. So here's, again, just to show you that this works, here's Montezuma's Revenge. It scored 0%. This is expressed in terms of percentage of a human professional. They hired someone to play these games for a year at DeepMind. I volunteered for that job, but they didn't hire me. And this is the sort of percentage of how much better or worse the neural network did in terms of percentage of the score of the human. And it does as much as 2,500 times better to 0 for a few difficult games. And this was now 10 years ago, so the state of the art's much better now, but I think gives you a feel. Yeah, oh, it's good, yes. I mean, it's a little bit idiosyncratic. So this one was, I mentioned that, so the reason Pac-Man is hard, it's a technical thing. Well, basically the computer didn't discover that sometimes you can eat the ghosts. And also I think there's a thing where the screen flashes and so it can't see anything half the time. So so speaking of why it's important to have a formalism here, the Markov decision process basically says there's a sort of conditional independence property that the future state is conditionally independent of everything else given the current state in action. So the current state, if that's the video screen, has to tell you everything there is to know about what's coming next for this whole thing to work. Or another way of saying that is you have to contrive that the input to the learning system tells it everything it needs to know at each step for all of these, for this recursive Bellman equation that Ruben mentioned, the form of the objective function to work. You need to satisfy this Markov conditional independence property. Pac-Man doesn't satisfy that because the screen flashes on and off when when you eat the pill that lets you go after the ghosts. And so if the screen is completely black, it doesn't tell you anything, and it sort of breaks the system. So these are technical things, but that's probably mostly true. Any other questions? Again, we're really just sort of setting up intuition here, and I hope that this, through sort of repetition and layers of the onion, this will become clearer and clearer. So putting it together then, and so taking it toward thinking about the brain, if we start with this idea that there's sort of this rough dichotomy between mental simulation and learning or figuring out a model of the world and using it to evaluate actions through sort of working out sums of future rewards, maybe not exhaustively and maybe not exclusively, but that's basically a building block. That model-based learning, as I'll come back to, is associated in neuroscience with anticipatory activity, sort of about future situations. We'll talk about spatial paths in hippocampus a lot. And behaviorally, it's associated, and I think someone mentioned this last night, with sort of flexible planning, right? Or flexibility, ability to figure out what to do, novel shortcuts, and so on situations. So that's one thing. The other thing is this model-free learning that, again, is going to be, I think, the topic of now's lectures. It's for a long time going back to sort of seminal work by Wolfram Schultz and Peter Dayan and Reed Montague, associated with these reward prediction errors in dopamine. And as I'll talk about next, behaviorally, this is associated with phenomena of habits and slips of action, sort of failures of flexibility, where you inappropriately reuse behaviors that are learned in other contexts and things like that. So there's sort of two building blocks for how to sort of try to evaluate this function, solve this sort of long-term credit assignment problem of hooking up actions and rewards. And the claim, going back to work we did a long time ago, and again, you could be uncomfortable with this, and we've softened this idea now, but is that the brain somehow implements kind of both of these approaches in parallel. That on the one hand, you might have model-free systems that are well described by dopamine, but you also have this kind of mental simulation, and somehow the brain's trading those two approaches off. Okay. That was the intro. So let's start trying to make this concrete in terms of sort of data about animals and humans solving different tasks. So the idea of model-free learning actually goes back in psychology even before this work on dopamine. So in the about 100 years ago or more, Thorndike was identifying sort of the laws of psychology, as it were, of behavior. And he had this idea called the law of effect, which was basically the sort of reinforcement principle that if animals did something that resulted in getting reward, then they would do it more often later. And so this sort of simple idea of sort of stamping in actions that ultimately result in reward is a sort of model-free learning idea. You don't have to learn the map of the maze, you just learn that if you make a bunch of turns, you get cheese, then you'll make those turns again, right? So that idea was a sort of a live theory in psychology. And in the 90s, there was this work on dopamine, again, that we're going to, all of this is a little out of order because I'm trying to leave now his space, but there was this work on dopamine in the 90s that showed it carried these very suggestive prediction errors that looked like they were appropriate for this kind of temporal difference learning of value functions in long-term, in sequentialization problems. And it seemed like that kind of all went together, right? But one thing that even goes back to the psychology is that if that was all that there was, it makes some weird behavioral predictions that animals and humans should sort of make some strange mistakes in certain situations. I'm going to unpack one of those in a sec. So the idea is, if your decision variable, if what you do is you learn, right, and you don't learn all of the things step by step that give rise to it, then if something in the world changes that sort of invalidates the deep in that sum reward should be, then until you kind of relearn experientially, if what you do is you learn that cue experientially by taking actions and seeing the rewards they lead to, which is basically how model-free reinforcement learning works, then you should be blind to those changes even though you know about them. Your actions should ignore them, and you should make weird mistakes. And that's sort of prediction of these model-free theories that you can sort of test. So my example of that is, so this is my preference function. So I like sushi better than this sort of flat hamburger here. And so because of that, if I was sort of, when I was at NYU, if I was standing out on the street, I could go to McDonald's or I could go to Nobu, which is a fancy sushi restaurant. And because I liked the sushi more than the hamburger, I would go to Nobu more than McDonald's. And that was true, except one day I opened up the newspaper, and they had like, this is the weirdest thing, they had snuck into, or snuck out of all these sushi restaurants with bags of fish. They like stole it, or I guess they bought it and then took it out, sent it to a lab, and it was basically like poison, right? It was so full of mercury. They had this graph from like the fanciest sushi restaurants, and they graphed the amount of, well, they found the amount of sushi, the amount of fish in the sushi, the amount of mercury in the fish was poisonous and terrible. And they had this graph for women of like the amount of sushi they ate versus the mercury in their blood. It's women because it's, you know, an issue for pregnancy, and it was just astonishingly terrible. And so having read this, you know, now I prefer the hamburger, right? So the question is, if I go back out on the street now and I'm trying to decide like which subway to get on, right, to go to the restaurant, where should I go, right? And at some level it seems obvious that I don't want to go to Nobu now because I don't want the fish. I should go to the other subway. But it's important to say that that's true because of this sort of chain of reasoning that goes through the subway to the restaurant, to the menu, to the fish, to the mercury. And if I don't work through that whole chain of reasoning, and I just have a Q value in my head that says getting on this subway is better than getting on that subway, then reading about fish in the New York Times isn't going to change anything. I'm going to have to go all the way down there, get the fish, and realize I don't want it, right, and experientially learn. So if I'm a sort of model-free learner, just very abstractly, you might expect that I make this sort of mistake where I know I don't want the fish, but I don't, because I'm not using a model to connect the choice of the subway through the menu to the outcome, the knowledge about the fish isn't going to update my preference over subways, right? Well, it just has yeah, it's because the information are not grounded in the chain of events. So another way of saying this, so here's a sort of simplified version of the Bellman equation, right? If the expected value of going here or here is going to be sort of an expectation over something, this is sort of like the menu, right? If O is the different, you know, outcomes, so if action is the different, leads me to the different restaurants, the O is fish or hamburger, and they've got different values, then there's sort of two ways to solve this problem, right? The model-based and model-free. Like, if what I did was I learned the menus of the restaurants and sort of the subway map and stuff, and how much I want fish or hamburgers, then I can stand on the street and I can think about, hey, if I go here, I'll get the fish and I don't want the fish, and that works out to a low value, and I'll get the hamburger and that works out to a high value. Yeah. Exactly, that's why the model free can't do it. Ah, well, yeah, I agree. So that's, you would have to, in order to even relearn, so there's, I guess, a second question, which maybe this example is slightly artificial. You have to allow for the fact, if I get here and eat the fish, I have to somehow disfavor that reward through the model-free system, right? It's true that it's not. I think that's a fair criticism of the thought experiment. Yeah. Yes. Yeah, so that's roughly a approach called the successor representation, and I think we'll talk about that on Saturday. That is that's a sort of an intermediate approach to this problem. You can think of that group as being a little bit like a world model, so it's a world model that might skip multiple steps. And so that also means because it bundles up multiple steps, it can also make mistakes if things inside that bundle change. And so that's indeed a whole other wrinkle. But that's very good reasoning. Yes, exactly. Good. Yeah. Of model-free learning. Yeah. So about the on-policy part. Yes, and we've tested that. You can fool people that way. That's another example. I'm going to show an example. I think what Ruben's saying, let's see if I can unpack this. What this is about to motivate is experiments where you train animals to choose between things, you devalue the reward, and you see if they keep making the wrong choice. That's one way to fool model-free learning, because these numbers, the expected future values, don't take into account the consequences in terms of individual outcomes. That's the logic. Ruben's also saying you can do more complicated things where you change the animals. If you think about a maze, if you change the later choices that the animal is going to make later in the maze, even if you don't change the outcomes, then that will also change the values. And that is something that we've used to fool humans as well. And maybe I'll show an example of that on Saturday. That's a slightly more complicated experiment. The ways you can, if to the extent that people are doing something like this or animals, you can sort of, you should be able to fool them. Is the logic clear? So here's the actual experiment. This is a sort of classic experiment. In some ways, it goes back to Tolman in the 50s, but this is a version that was popularized by Tony Dickinson and then Werner Belain, and they've done this lots and lots of times with rodents and sometimes other organisms. And the basic experiment works like this. I'm thinking I will actually switch to like pointing on the screen. So the idea is you train an animal to lever press for food, okay? And then the idea is you want to make the animal not want the food anymore. And so it turns out, this is something I learned, maybe you experimentalists can verify this is true, but I understand that actually rats can't vomit. Like vomiting is a recent evolutionary invention. And so if rats eat something that's bad, then it's really bad for them. And so rats have a very strong taste aversion learning, where even though they sort of make a living foraging on garbage and eating crap, they're still very careful about what they eat, because they have to be, because they can't purge it if they eat something poisonous. And so basically, rats are sort of very neophobic about food, and if they do eat something that makes them sick, they'll never touch it again. So you can take advantage of this by taking whatever the cheese, the particular food they were lever pressing for in the first step, and you can pair it with chemically induced illness, and that produces this very strong taste aversion response. And this is supposed to be analogous to reading the New York Times, but it's experiential, of course, that if the animals are then given the food, they won't touch it. They hate it at that point, and they do not want it. So that now you have a case where the animals learn to lever press for food, you put them back in the chamber and you ask, will they work, right? Will they lever press? And the control for this is animals who still want the cheese, right? Who haven't undergone this pairing. And the other important thing about this study is that to avoid new experiential learning in phase 3, you do this at extinction, right? You don't give the food. You just put them back in the box, you turn the lever off, and you see if they press it. So obviously, animals will press the lever, they'll get nothing, and they'll figure out it doesn't work anymore, and they'll stop lever pressing. That part's not surprising. But the question is there a difference between the animals who want the food and the animals who don't want the food in that process? Like, because if you don't want the food, you might never press the lever in the first place. You don't have to learn it doesn't work. But it's important that you don't give the cheese in the third phase, so that you avoid the possibility of the sort of relearning, that the model-free system can sort of relearn. I press the lever, I get the food, I don't want the food, I down-weight the action. Right? Is the logic of this clear? Okay, so the prediction of model-free learning is that animals, it's a bit of model-based learning, right? If the animal sits and thinks, if I press the lever, I'll get cheese, and cheese is good, and I want cheese, and now if I press the lever, I'll get cheese, and I don't want cheese, he'll stop lever pressing. Model-based learning can solve this. Model-free learning can't, right? So will you get this subset action? So, or conversely, can animals adjust flexibly their action selection policy to take into account their sort of motivation for the rewards? This is a sort of animal version of what in AI would be called a transfer learning problem, right? So this experiment's done tons of times, and the answer is it depends. So animals can do both things. So this is data from Peter Holland, but again, it's very typical. In some circumstances, what you see is animals who don't want the cheese lever press significantly less than animals who do want the cheese, here shown in white. And again, what this shows, this is a case where the animals have been moderately trained, so in the first step, they've maybe lever pressed for 3 sessions or something. What this shows is that the decision to lever press takes account of some kind of representation of the outcome. So we think of that as being like an internal model. It's dependent on whether or not the animal wants the outcome. So inside the animal's head, in some sense, affecting the decision to lever press has to be a representation of the particular outcome. That's what this shows. So that's sort of consistent with the predictions of like something like model-based learning. The behavioral psychologists have called this goal-directed behavior, where the goal refers to the cheese. On the other hand, if you have overtrained animals, so maybe like 20 sessions of training in the first step, then what you see is the animals who want the cheese or don't want the cheese lever press just as much as the animals who do. So they become insensitive to outcome evaluation. Now you might think that's somehow because they become, the manipulation doesn't work or something, but just to be clear, you can test, they do test, the animals don't want the food, they won't eat the food if you give it to them, and if anything, these animals should know even better than these animals that the lever produces the food. So it's not, they know each of the links of the chain demonstrably, and yet they still do the action. They're sort of working as hard for food they don't want as for food they do, right? So this is weird. This is this weird kind of slip of action, and this is the strange kind of mistake that model-free learning predicts, right? So what they call this in the behavioral psychology literature, Tony Dickinson and these guys, is habitual behavior. And the reason that is it's meant to be a sort of animal model of something I think we're all familiar with, which is that with repetition, sometimes actions seem like they become sort of automatic, and you sort of, you know, like opening Facebook or something becomes sort of automatic you do it sort of without even thinking through sort of repetition. And this seems like it's an animal model of that. But at another level, it seems like it's a sort of manifestation of these sort of different modes of computing the value of an action through a chain of consequences, right? Which is, again, the problem that Ruben set up in some ways. Is that clear? So the view of the behavioral psychologists had been that there were sort of 2 systems in the brain responsible for these 2 things. And again, this is part of why we started talking about model-based and model-free learning being distinct systems. And one reason they thought that was they paired these experiments now with lesions. And there was a classic series of studies from Bernard Bellane's lab, and Henry Yin was one of the major people. And they basically found 2 circuits, sort of cortical striatal loops involving discrete regions of cortex, striatum, and I think thalamus, which isn't shown in this figure, that seem to be differentially responsible for either of these 2 patterns of behavior. So that is to say, if you could, in one example, you could overtrain rats. You could get them to a situation where control animals are habitual. They'll lever press just as much for food they don't want as food they want. But if you take out the dorsolateral striatum or dopamine into dorsolateral striatum or associated cortical areas, you find that they never form the habit. Even after overtraining, these animals, unlike control ones, continue to be devaluation sensitive, continue to be goal-directed, like model-based in our terms. And conversely, there's a set of areas where if you take them out, and this is sort of medial prefrontal cortex and dorsomedial striatum sort of downstream from it, where if you take them out, animals still learn to lever press. It's sort of ropey. So this is a situation where animals will be devaluation sensitive. But here, you get animals who start to learn to lever press, but what they're learning is just the devaluation insensitive part, right? So they're sort of acquiring lever pressing, the sort of nub of it, the part of it that's the habit, and that develops slowly and grows, but they never get the sort of goal-directed part of it, right? And so it looks as though, from these kind of experiments, that you have sort of dissociable circuits that are subserving these two sort of modes of behavior, the sort of model-free part and the model-based part, as we would say it. Does that make sense? And I think it's telling in this particular figure, even the control animals after moderate training, when they don't want the food, press the lever some. It's as though there's a little bit of a habit that sort of started, and that's what you have in these lesioned animals as well. You have sort of that same level of lever pressing. Okay. Yeah. They've done it a few different ways. They've done it with inactivations. I think the original ones, I think the ones I'm showing are before learning, but I think it basically works. It's a good question. There's a more complicated story. There's some aspects in some places if you inactivate, then you can affect acquisition but not expression stuff. I can't remember the whole. This was a very long and continuing literature, but that's a good. I think these are before learning, the sort of core results. Yeah. Yeah, well, I think that's the, in some ways that's the paradox of these experiments, right? That, but your experiments too, right? Like when I drive to work every day, right? And I turn right at the stoplight to get to work, and on Saturday I'm going to the supermarket, and I need to turn left. But every Saturday I turn right, by mistake. I've done it 1,000 times, right? So it's not that I don't know, it's that as you go from the undertrained situation to the overtrained situation, behavior becomes automatic in some way. You get this dominance of this, what they call the habit, right? So the habit doesn't dominate early, it dominates late. It's not in control of behavior. Yeah, I think that's right. And there are various, and again, actually these inactivation experiments, there are ways where you can bring back the model, and people, right? People catch themselves. Animals aren't so good at catching themselves, but one reason it's been hard to do these experiments in people is people have slips of action, and then I turn right and I quickly turn left, right, and they correct. So it's not that you don't have the model, it's that it's somehow not engaged in behavior, right? You're not using it, and again, that's what led to these kind of ideas that there were parallel systems, which again, I'm not, while I was associated with them at one time, I'm not a strong advocate for a very strong dichotomy there, as we'll see. Good. Let's unpack that, because I think what you're pointing out is a really important question. I want to come back to it in one sec, but I want to say one thing, which is why is this dual system idea like such a, I think this idea that there's a sort of a fast and slow system, or an automatic and deliberative system, or this goes back to Plato. It's all over behavioral economics, as I think we'll hear from Lucia tomorrow. It's very common in psychology. It's common in social psychology. It's a very popular idea, in part because it seems like an easy way of thinking about why we might be sort of two minds about various things. And so people bring it up in social psychology for racism and moral dilemmas, and people bring it up for drug abuse and other sort of compulsive disorders and sort of psychiatry. And the idea that people have in mind is that you have some kind of healthy, in the healthy case, you have some kind of system that makes common behaviors automatic, frees up cognitive resources or something. That gives rise to habits, but also these kind of slips of action, might be associated with sort of self-control and willpower. And there's this sort of program that particularly goes back to Everett and Robbins, who were involved in these rat experiments on habits, trying to argue that this might be a sort of foundation for compulsive disorders in psychiatry. So one of the big questions in mental illness is that for the most part, the symptoms of mental illness aren't really grounded in brain mechanisms, right? Or even psychological mechanisms. We don't really know you know, if you go to the doctor to get diagnosed with depression, they diagnose you with self-reporting a list of symptoms, right? They don't have a mapping from those symptoms onto what they call the etiology, right? The tissue that's causing it. And so what Everett and Robbins had hoped was that these experiments showing this sort of dichotomy between a more habitual system and a more deliberative system, goal direction habitual, might help to think about why it is that people will, you know, take drugs that they know are bad for them, right? And that, so that idea is at least one sort of live idea, say in the case of drugs of abuse, that they might be sort of involved in training up kind of bad habits, and those bad habits then sort of dominate and become unbalanced in some way. That's a sort of prominent way of thinking. We'll come back a little bit to testing that a bit later, but that's kind of the motivation, or part of the motivation why people are excited about this kind of thing. But I think one thing, and this is the question I think you had, is I think if you think about this type of system or this type of architecture, it really implies, it seems a little crazy if you think about it, right? So like if I was going to build a robot and I wanted to have it make decisions, then I wouldn't want to build a robot with like two different systems for making decisions, because then I wouldn't have solved the problem making decisions. I would sort of compounded it, right? Because now either they want to do the same thing, in which case I don't need two, or they don't, in which case now I have to decide which one to sort of trust, right? And so there's a sort of, once you have multiple routes to choice, if that's what you have, then you have this sort of arbitration problem, which is, you know, when should I use the deliberative system and when should I use the habitual system, right? When should I retrieve action values and when should I compute action values? That's another way of saying that. When should I think through steps? And I think this model-based, model-free idea, again, helps us to sort of get a handle on that in kind of a sort of resource-rational kind of way. And the idea is just that you have this sort of cost-benefit trade-off, and we'll go into this in much more detail maybe on Saturday or the end of today, between thinking and acting, right? So deliberation is costly, right? It takes time. I've got to stop and think. Sometimes that's going to be helpful because it's going to help me make better decisions and earn more reward. And sometimes it's not. And so, in particular, if I'm highly practiced in a stable environment, if I've been lever pressing for food 20 days in a row, and you know, every time that's been good, on the 21st day, maybe it's not worth my while to stop and think, what's this lever going to get me? It's going to get me food. Do I want the food? Yes or no? I should just do it, right? And so building in a system, I think maybe this is the answer to the intuition why this makes sense, that you want to spend sort of thinking resources, sort of flexibility resources when you're not sure what the best course of action is, when you don't have a lot of experience to sort of squeeze the best decisions out. But when you're highly practiced, you can just act, right? And so we sort of wrote down a model of this, a sort of toy model of this, and Mehdi Karamati did a very nice version of that, that really sort of tries to sort of quantify what's the value of thinking versus acting in these sort of different scenarios, and can explain things like why, you know, overtraining causes a shift towards habits, and a number of other factors as well that come up in these experiments. So I'm going to do a sort of different version of that later, so I'm not going to unpack that here, but as a sort of piece of computational modeling that is enabled by this perspective. All right, any questions? Okay, let me do another example. This is the rodent spatial navigation one. So this is okay, let's see if I can make this play. Of course I can't. There it is. So this is a rat, and this doesn't show up very well. She's running, so there are feeders at the corners of the maze there that give her sucrose. This is double speed. And her job is to run back and forth to choose either one of the corners she's not at each step, and repeat. So she can go, and it's hard to see, there's barriers that make the paths between the different feeders longer or shorter. And the feeders are programmed to provide reward or not with different probabilities. So sort of like one's 20%, one's 80% or whatever. And then the idea is, these experiments were done by Tim Krause and Josh Burke's lab, and actually they're very similar to an experiment we saw yesterday from one of you in the student presentations. So these are experiments in which the animal has to learn sort of routes to maximize reward. In the environment is changing, so every once in a while, they either move the blocks around to change the distances, or they reprogram the feeders to change the amounts of reward. And so the animals have to sort of continually relearn what to do. Yeah. So the different probabilities that they can be anything between, I think it's 20 and 80. But they're fixed. They're fixed, but change sporadically. Yeah. And they have to alternate. No, they don't have to alternate. They have to not visit the same one twice in a row. So they can, for instance, cycle around in circles if they want. They have to always choose one of the two that they're not yet choosing. But the reward is very stochastic. So they have to estimate the reward probability under the possibility that it's changing, and while also balancing that against the distance. They can go ABC. They could go AB, 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 AB. They just have to. They have to every time. Because your third point is included, so they can go up and come down to the right. They could do that. They could do AB. They could cycle back and forth between two, but they don't have to, right? They always have. Sorry, there are three, and they can. So they always face a choice between two at each step. That's the idea. Okay, so that's the task. So this is sort of a dynamic kind of grid world foraging task. And the first thing we can say is that the animals can do this, right? So if you just look at their gross behavior kind of block-wise against the true reward probabilities and the programmed reward probabilities and the true path lengths, then the animals are sensitive to both. So they're more likely, when they're choosing between ports A and B, to choose the one that has a higher relative probability of reward than a lower one, and they're more likely to choose a shorter path length than a longer one. That's a regression that shows the same thing. The dots are animals. And this implies the animals are sort of learning, right, by trial and error, right? So this is, overall data, but they must, trial by trial, somehow be figuring out what to do. So one way we can look at that, to get sort of a maximally different view of what's going on. So this is the sort of global view of the behavior. We also look very locally at the behavior. Let's think about cases in which the animal faces a choice between A and B, right? And so he gets to here, and now he's back here, and he's choosing between A and B again. And we're going to ask, what's the chance that he chooses port A again as a function of whether he got rewarded or not on that trial, right? And a bunch of control variables. And so the answer is, not surprisingly, that if the animal runs from here to here and gets rewarded, and now he's back here again, he's more likely to go left again, right, than if he wasn't rewarded, okay? So, yes. Yeah. Yeah, but only occasionally. The animal, so sorry, they're fixed for maybe 50 trials in a row or something, and then they change. So the animal has to be on his toes, so they're noisy. So any particular time he gets to even if he gets to a good port, he might get rewarded 60% of the time. Yeah, I mean, well, the task is to earn as much reward as possible. Yeah, so they want to balance 60% against how long the path is, and yeah, So there's also the fact that going from one place to another is longer, than there's a distance factor as well. But yes, the reward part is they want to choose the more options. They have to figure out what those are, right? We can see on average they do, but the question is how. Well, so all we're saying is, so over here what I'm saying is if it's associated with a higher chance of reward, they'll choose it more. Now I'm going to zoom in trial by trial. I'm going to say, let's look at 2 trials in a row. What does the animal choose as a function of whether he gets rewarded or not, right? So if you think about now trial and error sort of learning, when I don't know what the probability is, you would think that there would be, overall, you should make a choice more if it's followed by reward than if it's not, right? So that's what's plotted here. So the animal starts at this, starts at some corner, chooses a port, and it gets rewarded, or not. And then the question is, how likely is to make that same choice the next time he's offered that option, right? Well, no, it's every trial. But it doesn't matter. We're just conditioning on the previous reward, right? So the question is, now looking very locally, how does the animal's choice depend on the reward? If you do that over and over again, then you'll tend to choose the better thing, right? That's the idea. Yeah, yes? Yeah. So do they tend to choose the thing that they chose last time also? Yeah, in general, yes. So so they're different. We can fit, more complicated learning models to the animal's behavior and see, and there's a whole part of this paper where we do that, and we take account of all the different things that affect the choices in terms of the history, and choice history is one of them. But a huge effect, which I'm just visualizing here as the sort of most important piece of it, is this sort of win, stay, lose shift, right? That they tend to revisit options that are rewarded, okay? Then revisit them less if they're not rewarded. Yes? Um, well, oh, I see. Do I think they have figured it out up here, or do they do it down here? Is that? Yes. Um, we actually think, yeah, we actually think that there's stuff that goes on. This is what I'll come back to if I get to hippocampus. Probably not today. The stuff that's going on in the rat's brain here that's thinking about what he's going to do next time that he's here, right? So so I should have said, the reason this whole task poses an interesting problem is exactly that. The animal's going to get a reward over here, and then he's going to go over here, and he's got to decide what to do, and somehow he's got to connect this event over here in terms of long distance of space and time, right, to make a choice over here. So there's literally this kind of bridging of an action that he's making, down here to a consequence he gets over here. I think that's your question, if I understand it. He's going to get a reward here, but he's got to sort of take account of that somewhere else in space, 10 seconds later, right? And this shows that he does, right? So he takes this action more if he was rewarded for it the last time, right? Which was 10 seconds ago or something, okay? And again, the idea is that you sort of string together this kind of thing, and this is just one narrow window into it, but you string this kind of thing, and it gives you the ability to, this is sort of one very local view on the animal's learning, which port is more valuable, right? Yeah, and the behavior also depends on the next last experience and the one before that and so on, but less, right? So it's like a running average, and that, if we fit a full model, it's a longer story, but this is just the simplest view of it. But the thing I actually want to expose here is not that. It's the model-based, model-free distinction in the following sense. So I've mentioned, and we'll talk a little bit more how it actually works now. Model-free learning basically learns experientially. It says if I take a particular path, I get rewarded for it, I can reinforce that path, right? I can learn experientially that running this way and turning left or whatever is more valuable or less valuable depending on whether it gets rewarded or not. So model-free learning predicts this pattern. Model-based learning also does, but an alternative possibility is, let's say the animal runs from here to here, gets rewarded, and now runs to here. Now he's taking an action which is not the same. He's following a different trajectory than the one that resulted in the reward. And so the question is, does the animal still go here more often if this was rewarded than if it wasn't, right? So is he able to infer the consequences of that this path has more reward for an alternative trajectory, right? So that would be like that would be an indication he's doing something more model-based. It's not directly experiential in the sense that he takes some action, he gets reward for it, you can do that action again, that's sort of simple, but you get reward, can you infer that you should change your preference over some other action altogether? Yes? I think so, yeah. I mean, what do you think you might not understand? Oh. Yeah, no, I think the animals are good at that. I mean, you can see from the gross data that they're good at it. They understand. There's landmarks and stuff as well. So there's something hanging on the wall. I can show you a picture of they actually try to make sure the animals can stay. They have place cells that we'll see that are tuned to the various locations and stuff. Yeah. So there's I guess all I'm saying is, I think, what I'm saying is, for this reward, this reward can have an effect on a choice starting from the same point through experiential learning, right? And it does. If it also has an effect on a choice from a different starting point, that's not experiential. That would have to be through some kind of model of the routes, right? And it does as well, right? But how do you know that they haven't learned beforehand if their environment is from bottom right to up? Yeah. How do you know they're testing right? Yeah. So because I'm only showing you the one trial back, they're about conditional independences, that in general the animal's action depends on the whole history of things, and the knowledge you're talking about is embedded in that. So there are two answers to that. One is that there's lots of lagged indicators in this regression that try to take that out, and the other is that we fit much more elaborate reinforcement layer models. And all I'm visualizing is the one trial back effects. But that's a good question. Yeah. Yes. So that is an interesting question. So there is some, so that it's not the center point, but there's some twisty path from A to B and from C to B that at some point come together at a common point. So depending on the particular maze configuration, where the choice point is, it's a little bit hard just from trial-wise behavior to make the argument I'm making, right? Because if this were the geometry, the animal could just run to here and then decide what to do, right? Sometimes the choice point is before the common point, and we can when we look at neural data in a second, we can make sure that we're looking at non-overlapping parts. Yeah. Yeah, to the common choice point. that depends on the topography of the particular maze setup. That will be true for some and not for others. I think the full answer to that question is to look in the brain, because you can look at non-overlapping parts of the trajectory. But it's a good point that this logic is, from the gross behavior that I'm showing you, is not always, because you don't know when the animal makes the decision, and there are at least cases in which he could have made a decision at a common choice point. But I think not always. So for instance, depending on where the choice point is, there could be no overlap, or it could be you have to commit to going to one side before the overlapping part. So the conclusion from the plot at the right is that the indication for the behavior is that animals can propagate value long distances over space, right? And they can do so both along experience trajectories, but also apparently, using the sort of spatial map along non-experience trajectories. So that's what the green shows. The animals which they lose shift with respect to corners, even when they don't, when they didn't experience that trajectory leading to that reward, right? Yes, and they use that, putting it together with the path to plan the action. That's the model-based part, right? That's the idea. This is supposed to be the signature of that. Right? And if they were completely model-free, they wouldn't presumably be able to do that. That's the idea. Yeah. Yeah. Yeah, so in general, they're pretty well modeled as a sort of exponentially windowed running average. So they weight the most recent reward most heavily. This is true in a lot of learning tasks, and Ray has worked on it. A bunch of us worked on it. So because the rewards are stochastic and because they're changing, what they do, I didn't show the equations, but they treat the value of the corner as sort of an average of previous outcomes, with the most recent one weighted most heavily. And so that means that, yeah, even if they get a bunch of rewards in a row, if they miss one, they're a little less likely to go there again. If they miss a few, they're much less likely. And that's what the prediction error learning model, the reason I skipped this is now we'll talk about this. Prediction error driven learning models, that's how they learn, right? They compute a prediction error between the rewards you expect and the rewards you got, and they increase or decrease the value according to that, right? And that's what this is showing. Maybe I should have shown that. Again, I tried to trim the part that overlapped now stock. Okay, any other questions? So the behavior is showing us, again, I think sort of signatures of what looks like model-free or possibly model-free and model-based learning, or the ability to propagate value kind of experientially over distance in a sequential task. Okay. What does this look like in the brain? So in this experiment, Tim was recording dopamine in the nucleus accumbens using the fluorescent indicator D-light. And the first thing to say about dopamine, and this is going to be the topic of now's talk, is that it famously has these prediction error responses, right? So I can't not say this anymore. When the animal gets to the corner and gets the reward, you see this phasic burst of dopamine if he gets a reward, or a phasic pause in dopamine if he doesn't get a reward. That's supposed to be associated with the idea is that it reports a prediction error, the difference between the reward the animal expected and the reward he got. So the reward he got is high if he gets a reward, and 1 if he gets a reward, and 0 if not. And then it's further modulated by how much he expected it. So this is just broken down by the true reward probability, which the animal is sort of learning. And this is just very typical data. You have a stronger positive response to reward that's most unexpected. That is when the reward probability at that port is low compared to high. And you get a negative response which doesn't separate well in the case of omission. So this all, I think, now will show you much more data like this. That's the standard story. Again, going back to Schulstein, Montague. And that story and sort of temporal difference learning prediction error story of dopamine was about how this signal might be used to assign value to locations that you encountered previously along the trajectory for this sort of experiential learning. And depending on sort of time scale constants, for those of you who are sort of aficionados in this, something called a eligibility trace, it might stretch along the experience path a long way or not. But the other thing that it's supposed to do, and again, I think now we'll show you this, is chain backwards. So if I run from here to here, I get reward, and that tells me that this part of the, that lets me assign value to sort of locations on the maze here, and the next time when I run from here to here, you can get some dopamine there, and that will help you chain value further backward along the path and so on. If you run along the path a number of times, you might see, theoretically, this has been hard to show, you might see value propagate back experientially along the path, okay? So that was a sort of, that's the sort of model-free learning dopaminergic prediction error story of how learning could happen in this task. And again, what that wouldn't do is propagate value to paths you didn't take. Yeah. No. I mean, it's been a long argument whether or not there is. We have some in this experiment finally, and now has another experiment separately that shows it, and he might show you that as well. But it's been a long time coming. So that's, we're gonna, I will show you that in a minute, but, or I might run out of time, but. And again, this whole story, while it might be true, isn't enough to explain the behavior I showed you, right? It doesn't explain how the animal figures out. It might explain how this value chains all the way back to the previous, to the starting point. It doesn't explain how it chains back to here when the animal is deciding how to get this way, right? Is that clear? Okay, so here's the next part. The next part is another thing we'd like to do is measure the animal's value expectation now over space, right? So it turns out, and it's a good thing Nao's not here because it's controversial how to interpret this. This is the famous part of dopamine. I actually agree with him, but it's a long story. My co-author Josh doesn't. The famous part of dopamine is this phasic prediction error burst. But you can see in this figure that something else is going on. There's this sort of ramp as the animal gets closer to the reward. And this is typical, particularly in spatial tasks, kind of extended tasks, rodent tasks. You often see this reward-locked or event-locked phasic responding, but also this slow ramp that's much lower magnitude. If you zoom in on that slow ramp, it's been argued that ramp's proportional to the animal's value expectation. That is the V or the Q that is supposed to be learned in these models, right? So why do I think that? Or why has this been argued by people like Sam Gershman? One thing is that it ramps up. So as the animal gets closer and closer to the reward part, it ramps up. So that's like this time discounting function that was in Rubin's version of the equation. You can see the discounting by distance. So that might explain how the animal trades off distance against reward in this experiment. The value ramps up, if this is value, as you get closer to the reward. It also ramps up higher if the reward is higher. So this again is just broken down by the probability of reward, the objective probability, program probability of reward. It ramps more as the animal approaches a better port than as the animal approaches a worse port. So this looks like the dopamine signal, the sort of continuous one in the rest of the maze, the part that's not sort of reward locked, is for some reason proportional to value. Yeah. That's right, but it's an expectation, right? So the value function is an average. So that's why it would be higher for 60% than 30%. Well, so it's always the case that as they get closer to the port, they're getting closer to the chance of reward. But the question is, so the value is, in Rubin's terms, always positive, right? So I'm going from, let's say I'm running towards a 30% chance of reward. As I get closer and closer and closer, my value function ramps up from 30 discounted by a number of steps to 30, or 30%, or 0.3. And if I'm running towards a 0.75 reward, it ramps up to 0.75, right? So it doesn't ramp down as you get closer to reward, even if it's a low chance of reward. It just ramps up slower, and that's what's shown here. Does that make sense? Sure. Oh, that's forward, sorry. But so this is after all of this is happening before the reward, right? So this is as the animal's approaching the port. Once he gets to the port, if he doesn't get reward, the dopamine neurons pause. That signals a negative prediction error. That's supposed to reduce value the next time along the path. He doesn't know which one. So yeah, so there is, if he doesn't get the reward, there will be a mission, but it's you can actually see it here, right? Those plots are cropped here, right? It's before the animal knows if he's going to get reward or not, for sure. Yeah, good question. Yeah. 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 Yes. Yeah, yeah, that's a whole, let's see. Yeah, this is just, we're going to dig into more detail, and the paper digs in much more detail into this, but this is just the simplest possible visualization to show you. So the covert variable is going to be correlated to the overt variable. We have a very elaborate model of trial by trial value and how it's changing with experience, and we're matching that up to the signal trial by trial. I'm going to show you a little more of that here, but that is the program is that we have a trial by trial readout of value along the path, and we can then try to understand how it changes with the animal's experience and fit that to models. That's the idea.
I was just wondering whether the omission the omission part, which is pretty independent in this case of reward probability, could be understood as something like that. I mean,
you mean why this is doesn't? So the issue here, there's a whole discussion of this, and again, this is probably a better question for now. Why doesn't this separate well? It's a sort of floor effect. So the dopamine firing rate is low, and so the negative excursions are not very well. They sort of
but in the classical experiments, there is a
rectified.
little bit of separation, right?
I'm sorry?
In the classical experiments by Schultz, yeah, there is a little bit of separation, right?
But if you, I could show you a plot. It gets sort of rectified pretty fast.
Right,
like
right,
it's zero. If you think prediction error is linear, the dopamine spike rate is linear prediction error. You sort of hit zero pretty fast. I think that's what you're seeing here. But
right, okay.
But I'm actually not. I'm going to focus on modeling this part and not this part today, or tomorrow, because I think I'm out of time. Yeah. Okay. Yeah, I can finish this section in 7 more minutes. That's great. Let me tell you a couple more things. This is great discussion, and this is all kind of leading in the right direction. First of all, this is an average, and this is with respect to the true reward probabilities. And as Rubens pointed out, they're not, the animal doesn't necessarily know that on every trial. We do have a computational learning model, trial by trial, of what we think the animal thinks the value is at every location and every trial. And so we can match that up. And so here's 2 examples where the animal takes the same path on individual trials. This is dopamine on the right, and this is the sort of model predictions on the left. And so they sort of the trial by trial excursions in these signals match up. I hear a lot of sort of discussion. I thought maybe I lost people, and other questions or? Okay. These model-based and model-free kind of layered on top of each other, and I'll show you why I think that's the case. So I want to say two more things about this. There's a big controversy, and Nao's involved in it, and again, I kind of agree with him about why it is that dopamine looks like it's signaling something else. So again, the big story about dopamine is what it does at the time of reward. Whether it's really, this is a side effect of that what we're looking at in terms of these value ramps is a side effect of this reward prediction error, or it's another mode altogether. There's a disagreement between a number of people about that. For what I'm going to tell you today, and Nao has a strong feeling, and I kind of buy it, that this value is a side effect of prediction error signaling for reasons that he can explain, but it doesn't matter. The point is that from the neural activity as the animal runs around this maze, we can, if this for whatever reason is proportional to the animal's value expectation, we can study how the animal propagates value expectation over space in response to his experience, right? So this question of he gets a reward at some corner of the maze, and he knows about that in other locations, we can read that off when he's in other locations because we can see, do these ramps move around, okay? Do they move up and down? And where do they move up and down? Is that clear? So that's the question. And the particular question is, do they move up and down along the experience path or also along other paths as well? Okay? And the answer is both. And I can just show you that, and maybe I'll wrap up for today. So there are different ways to visualize this. Again, we have very elaborate analyses and models, but I just want to show you a visualization that gives you the feel. This is sort of similar to what I showed you for the behavior. So the animal runs from port A to port B, and then from port A to port B again. And we're actually going to look at situations when he runs the same path 3 times in a row. And on the first one, he's non-rewarded, and the second one, he's rewarded, or vice versa. And the idea is, if he's not rewarded and then rewarded, you see this value ramp as the animal approaches the port. It's lower after the non-reward, the next, till he gets to the port. Now he gets rewarded, he runs it again, and now it's higher. And you can see it's sort of higher all along the path. It looks as though, comparing running a path and getting the non-reward to running a path and getting a reward, the value function moves up, right? And it doesn't just move up at the end, it looks like it moves up the whole way. So this reward, this non-reward he got before this path, moved it down, and then the reward that he got before this path moved it up, and that causes these two lines to separate, right? Yes? It's for reward, it's following a no reward run. It's a little, so he ran before this path, which isn't shown. He ran and didn't get reward. Now he runs this path, and then he gets a reward, and then he runs this path, and then on the second run, following the reward, it's higher, right? So the reward moved it up. We can reverse those two events. Now this is the rewarded path, followed by, which is that, so following reward, he runs the dotted line, and then he gets non-rewarded, and then he runs the solid line, and it's lower. So a reward moves it up, and a non-reward moves it down. And again, what's striking about this is it's along the whole path. This is like a meter long or whatever. The value propagates all the way back, more or less, okay? So we can, and now we can just, so we sort of inferred that from the choices, but we can now see that in this neural readout of value as well. And the big question, of course, is, does that also happen along a non-experience path, right? And the answer is yes. It looks just the same. So now on the non-rewarded, the reward and non-reward are along this path, and then he next takes the other path and it's higher or lower depending on whether reward or non-reward preceded it, right? Yeah. Ah. So there's something like 10 animals, and there's something like 20 sessions per animal, and there's something like 200 trials per session. There's lots of trials, like tens of thousands of trials. The sub-selection involved in finding these sequences is a lot less. So I don't, off the top of my head, know. But at the end of the day, it's an average of 12 lines, one for each animal, and those 12 lines are an average of 30 lines, one for each session. Yeah. Um, what do you mean with something? Uh, yeah. 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 Oh. Oh. Yeah. I wouldn't draw any differences between these. They all look to me about the same. With respect to the error bars, I think the main point is that it looks as though these lines separate in all cases more or less along the entire length. I wouldn't draw any strong conclusions about the shape. Right. Sure. So, yeah, go ahead. Uh-huh. Uh, yeah, you could do it that way too. This is trying to control for one more trial back because there are sequential effects. And this is a point that we were discussing before. The animal's expectations are really learned over multiple trials in a row. And so by showing you this trial followed by this one and this trial followed by this one, we're just trying to control for more, we're just trying to have a little bit more specificity. But you can do it many different ways. And in the paper, what we do is analyze trial by trial value responses with respect to a full computational learning model that is propagating value around the maze on each trial from the whole history of rewards. Is that is the question, is this significantly different from this? I think it is. I mean, another way of saying is, I think that maybe one way you're, one comparison you might be asking for is the blue line here different from the red line here? Oh, is this significantly different from this? It is at some of the points. That's what those stars are. So they're a little small. These are points where those two lines are significantly different. Is that the question? Yeah. So the answer is yes, somewhere. Yeah. And then I think this is a sort of aggregate of across the whole lines. Are they different? I think there's one more question. Um, yeah, we've tried lots of things. It becomes hard as this question of how many trials do you have. It becomes hard. You get smaller and smaller numbers of trials if you literally try to just enumerate different histories. And so what we do instead is we use these learning models, which I didn't write down, in part because I think now is going to show them, where we compute the value as a running average on every trial, no matter what the history was. We compute the value as a running average of previous rewards. And that allows us to use all the trials and then see that the activity is proportional to the value across everything. And that's also true. But I think this is a useful visualization to give you a intuition why it works. Yes? But yeah, but importantly, that value is accessed all over the maze, right? So then the question is, how does that happen, right? And that's sort of the rest of the story, right? What's that? Yeah, exactly. And that's the next part of the experiment, right? But the important thing is you couldn't do that if you were just using model-free reinforcement learning, right? So I think I'm going to quit here. Let me just, so we also see the model-free reinforcement learning, this sort of bumps moving backwards, but that's actually not that important for today. Let me finish this up by saying, by using this dopamine ramp, we can directly visualize this credit assignment over space. And so we can see this kind of model-free learning along paths, but we also see that value moves around the maze over long distances, and that affects choices, and not just along experience paths. And so this looks like a signature now in the, not just in rodents' choices, but in the rodent's brain, of sort of model-based credit assignment over the map. And next time we'll talk about how that works in the brain. Yes? Sort of. So I think everybody agrees that it's proportional to value. The question is why. So there's a big fight, and I actually think now might go into it. But there's a strong argument to be made that the reason dopamine is proportional to value is as a side effect of prediction error signaling. And it's something that depending on how you filter and average and rectify, that prediction errors in the body of the maze when there aren't any rewards end up proportional to value. I actually believe that. My co-author Josh Burke doesn't, but whether or not you believe that, it doesn't matter. If there's a signal in the brain that's proportional to value, whether or not it's really prediction error, it doesn't matter. We're just studying how the value correlate changes, right? So I have no, for this particular argument, I don't have to take a side, although I actually do agree with Now on that. Good, thanks a lot.